Alright, I'm going to discuss how to graph a function using first and second derivatives. So my first example here, I have the function f of x equals 2x cubed minus 3x squared minus 36x plus 5. Not normally something that people would know how to graph. The idea here is that if you find the derivatives, the derivative tells you the slope of the tangent at any given point. And in particular, anywhere where the derivative is equal to 0, the graph has the possibility of changing direction. Doesn't mean that it has to, but it can. So I'm going to start out by doing that. I'm going to find f prime here. F prime of x is going to be equal to 6x squared minus 6x minus 36. Now I want to actually set this thing equal to 0, and I'm going to find the critical values. The critical values, of course, are the values of x on the graph where the derivative is either equal to 0 or undefined. So I'm going to set the derivative equal to 0. Now you can use the solver or the 0 button on your calculator if you're on the graph and calculator portion. If not, you need to be able to factor or use the quadratic formula. In this case, I noticed that 6 factors out. So I get x squared minus x minus 6. And notice in this case that that's going to be the quantity x minus 3 times the quantity x plus 2. We get values of x is equal to positive 3 and x is equal to negative 2. Okay, those two values are the so-called critical values. These are places where the graph may change direction. Okay, at this point I put together a little number line, and the whole idea is to illustrate whether or not the graph is increasing or decreasing over different intervals. So going to create something for f prime and x, and I've got my little number line here, and again the only values I care about right now are the negative 2 and the positive 3 and what happens in between those intervals. So again, I'm worried about derivatives here, so we're looking at the derivative function. Of course, at negative 2 and 3, the derivative is equal to 0. The whole idea here is that I'm going to check values within different intervals. Okay, so first of all, I'm going to check a value over here on this side of negative 2. I'm going to find f prime of negative 3. And it doesn't matter. Any value to the left of negative 2 will work. F prime of negative 3 ends up being positive 36. And by the way, I only care about the sign. So sometimes if you go to the factored form of the equation, for example, if I put negative 3 in here, this value would be negative. If I put negative 3 in here, that value would be negative. A negative times a positive gives me a positive. So you can either find the functional value or just focus on the sign. Anyway, the point here is it's a very steep slope. That's a positive slope. Okay, really all I care about is the fact that the slope is positive, and you can draw a little line showing that the graph is going to be increasing there. Okay, I can pick a value between negative 2 and 3 and find the derivative there. 0 is between negative 2 and 3. F prime of 0 is equal to negative 36. That's negative. So the graph is going to be going downhill between 2 and 3. Finally, I can pick a value to the right of 3. So I can find f prime of 4. F prime of 4 is equal to 36. That's positive. The graph is increasing. Again, it's really only the signs that matter. So if you want to go back to this factored equation here and just substitute in and just think about what the signs will be, you really don't have to find the actual functional values. But there is my number line for my first derivative. Basically says the graph increases from negative infinity up to negative 2, decreases between negative 2 and 3, and it's going to increase after 3. Okay? Second of all, I want to know how the graph is curved. If you remember, graphs that do this type of thing are considered to be concave up, where the curved side basically points upwards. Graphs that look like this are considered to be concave down. And if you notice, for the graphs that are concave up, the slopes here are increasing. So if the slope is the rate of change of the graph. If the rate of change of the change is increasing, you're talking about a second derivative. So that's the next thing I'm going to find here. I'm going to take the second derivative of my function. It's f double prime. And f double prime is going to be 12x minus 6. And same kind of thing. I care about where that is equal to 0, because the places where the second derivative is equal to 0 are the places where my graph may have some kind of change in concavity. Okay? Positive second derivative is going to be concave up. Negative second derivative is going to be concave down. A second derivative of 0 basically just means that my line is going to be straight in that section, neither concave up nor concave down. So I'm going to do my little number line again. And I'm going to set the second derivative equal to 0. So that's 6 equals 12x. X is going to be 1/2. So that's the number I put on my number line. If I pick a value that is bigger than 1/2, for example, if I put something like 1 into this function, that would be a positive value. That would be concave up. And if I pick something smaller than 1/2, like 0, 0 minus 6 is going to be negative 6. And that's going to be concave down. So my graph is concave down until I get to 1/2, and it's concave up afterwards. And at this point, I can piece together my entire graph. And the main thing is just make sure you have labels of key points on your graph. That's really the most important thing overall. So to get an idea of the graph, and again, this is a sketch. This is not going to be a dead-on perfect graph. But basically you can go to your first derivative function and you can look at your critical values. And I'm going to plot a point at -2. And remember that this is a point on the original graph. So I want to go back to the original function. F of -2 is equal to 49. And if I can focus here, I also want to plot a point when x is equal to 3. F of 3 is -76. So I'm going to plot those 2 points first. So I have f of -2, which is 49. I'm just going to mark a 49 here on my graph, and at -2, 49, plot a point. And then down here at 3, -76, I'll plot a point. And again, this is definitely not to scale, but you'll see that I will label a couple values here. And now we look at the table. Notice that my graph is increasing all the way up to an x value of -2. And if we look down here at the second derivative, it's going to be concave down. So basically we've got something like this happening. It's going to be increasing all the way up to this point. It's going to be concave down. So basically this type of situation here. Okay. Then my graph changes direction. The derivative is 0 here when x is equal to -2, and then it starts going downhill. So this is a relative maximum value here. Starts going downhill. If you notice, the concavity stays negative until 1/2. So basically my graph is going to be negative with this concavity till about 1/2. And what will end up happening here is the concavity will change. Actually, I may have to adjust this just a little bit. Let's look at a few other things. Notice the graph increases after 3. And if we look at the concavity graph, it's concave up. So down here after this point, the graph is going to be concave up. It's going to be increasing, so it's going to be doing that kind of thing. It's also concave up on the other side all the way up to x equals 1/2. So we have something kind of like that. Basically, the graph kind of flattens out around this point. It wouldn't be terrible if you actually plotted that point on your graph as well. I didn't in this case. But the final function is going to look something kind of like this. And again, the calculus is helping us focus on the turning points in the graph. Certainly you can plot more points if you need to plot more points, but this gives you a general idea of what the graph looks like, and that's what's really most important. And by the way, if you want to see a verified version of this, I'm setting the window on my graphing calculator here from -10 to 10 and -100 to 100, and if we look at the graph, you can see it looks like that. So not a drastic difference between the graph I put together and the graph you can see there on the graphing calculator. So it does look like this worked out the way we want it to.